Okay, wrapping up. DeWitt's chapter 28, quantum theory, non-locality, our whole story about philosophy of physics and astronomy. We left off with a discussion of Bell's theorem or Bell's inequality, which is a mathematical result showing that quantum mechanics is incompatible with the locality principle. The locality principle is about as commonsensical as things could be. And so Bell's result is exactly what Einstein would have hoped for. It's like a descendant of the EPR thought experiment, really bringing out how nuts quantum theory is. Right? Quantum theory says there are pre-established harmonies. There are connections between twin particles such that what's going on with one of them instantaneously affects what's going on with the other, even though no signal could possibly get from one to the other. And so it really brings out how utterly incompatible with common sense quantum theory, which is an extremely well-tested fundamental theory in physics, turns out to be. We're going to bring this out. So if that's not super clear to you yet, hang in there for the rest of this lecture. I'm going to do one preliminary before we go into the experiments that vindicate quantum mechanics and undermine locality. Heisenberg tried to explain quantum theory, and I've used this explanation of his maybe in our first lecture on quantum. He said something that's true, it's just misleading. And since I said it, I want to bring out, in a way that we're now in a position to bring out, what's misleading about it. So, Heisenberg says part of what's going on in quantum is you can't perform a measurement on a quantum entity without disturbing it, right? We're looking at little tiny things moving really fast. And Heisenberg shows in detail, this is Heisenberg's uncertainty principle, that the way you have to disturb a quantum setup in order to determine the location of a particle prevents you from determining its velocity. What you'd have to do to determine its velocity prevents you from determining its location. This is 100% correct. I said it, borrowing from Heisenberg, I stand by it. It's just potentially misleading. So I want to make that point in two steps here. One is this whole idea of twinned phenomena shows that we can get information about a system without, in any intuitive way, directly interacting with it, right? If you know you're dealing with two identical twins and you know one of them is 5'8", then you know that the other is 5'8" without touching that twin. Similarly, you know that if you get an up-polarization for the particle that's been shot off to the right, in an identically configured detector, you'll get an up-polarization for the particle that's been shot off to the left. So, we can get information without bouncing a signal off of something. So that's the first point. Then the second one is that the uncertainty is not just that we are big and clumsy and quantum phenomena are small, quick, and fragile. That is true, but that's not the whole story. The uncertainty that Heisenberg has in mind, and I'm not correcting him, Heisenberg was trying to explain stuff in a non-technical way, and he's entirely right, it's just not the whole story. The uncertainty is in the math, not just in our size. The math, given a sort of minimal physical interpretation, says that if you precisely determine the velocity of a particle, the math represents it as a wave spread literally everywhere in the universe. So if you look at the math and give it the same kind of physical interpretation that you would be using to determine its velocity, you can say nothing about its location. That's a mathematical fact, not an experimental fact. So again, to recap, it is true that we are too big and clumsy to perform measurements on quantum phenomena without disturbing them. That is not the only source of quantum uncertainty. All right, now we turn to aspects experiments. Those of you who are listening to this lecture are going to save yourself from an embarrassing mistake that those people in the class who don't bother listening to this lecture and don't bother doing the reading, and there will be such people, if I ask about the aspect experiments, I'm going to get predictable bullshit. They're going to say it's about an aspect of reality. No, it's the dude's name. That's why it's capitalized. Alain Aspect is a French physicist. Astonishing experiments that he was able to perform in the early to mid 1980s. I was in college in the mid 80s. Please don't do the math. It was super exciting to learn the results of these experiments. I'm going to walk you through them and try to show why it's exciting. I hope something like that happens to you while you're in college. Feeling like our understanding of the universe fundamentally shifts while you're a college student is a super exciting thing. Having my physics major friends walk me through this over beers while I was in college was just a transformative aspect of my undergraduate career. I don't know what you're interested in, but I hope something is a transformative educational experience for you while you're here. Graduating seniors, perhaps we've failed you, and maybe you failed you, and you haven't had such experiences. But it's really cool to feel like your world gets rocked while you're an undergraduate student. All right, aspects experiments sure look like locality loses and quantum theory wins. How does that work? You start with particles in a twin state and you set up the experiment to ensure that there can be no influence unless it's a superluminal influence from one detector to the other. You have to make sure that the photons are not interfered with along the way. You have to set up all kinds of detection devices, sometimes mirrors, that alter things very rapidly and randomly. But the experiments have been done by many people many times. Aspect and his crew were not the first, and experiments like this are still being performed. The predictions of quantum mechanics about how much divergence you can get between the detectors are borne out, and those governed by the locality assumption are falsified. What does this mean in plain English? It means you shoot off particles in opposite directions, and a measurement operation performed on one particle seems instantly to affect the measurement operation performed on the other. So even though light can't get from one measurement to the other, it is as if the measurement being performed a microsecond later was informed by the one that was performed a microsecond before, even though light couldn't possibly get there. A different way of picturing it, the particles, even though they are fairly widely separated in space, act like one entity, like there's just one system. This raises deep questions about what space might believably be. We've seen some debates about whether space is substantivalist or relationist. Try to remind yourself about the Leibniz-Newton debate about the nature of space. But everybody seemed to think that if things are separated by space, you're dealing with separate things, that space distinguishes one thing from another. It's not clear that it does. You arguably should read entangled particles. That's what this is called. The twin particles are an entangled system. You should arguably see it as one thing, not two, even though they could, in principle, be in different galaxies. DeWitt uses causal talk, and he seems confident in saying that there's some causal relation between what happens at the first detector and what happens at the second detector. I am much less comfortable than DeWitt is in calling that connection causal. He in his book has not really talked about causation, at least in the chapters we've read. We read Hume on this. To put it mildly, it is not clear what causation amounts to. Surely if you treat causation as some stuff, some matter or energy being transferred from one particle to the other, then there's strong pressure to deny that causation is what's going on, because not even light could get from one point to the other. On the other hand, causation is also tied to explanation, and it sure seems like a big part of the explanation for why you get a down polarization on the second measurement is that you got a down polarization on the first. So we've got something like explanation without influence. How can that be? How can it, I mean, it's again like saying it's random what a dime is going to look like, but they all end up looking alike. Nobody really understands how best to describe it. You would think that this is incompatible with special relativity. If the explanation of what's going on at the first detector is crucial to the explanation of what's going on at the second, but not even light could get from the first to the second, you'd think that's a straightforward violation of special relativity. But it's not. This is where informational locality, which DeWitt discusses, is so important. Basically, matter or energy, and those are really two ways of saying the same thing, can be used to convey information. But this entanglement cannot be used to convey information. What Bell's theorem tells us is about the extent of the agreement between the results of the two detectors. The actual up, down, left, right, whatever you want to call it, the actual results are random. It's the extent of the agreement that is determined by quantum theory here. And so since all we can control with our detectors is how often we agree, we can't use this to communicate. In order to communicate, you'd have to use plain old-fashioned slower than light stuff and bring the two together in order to compare notes. All I can learn if I'm more than light speed distance away from you is something about how much our recordings agree, but that's not enough to send any information. And so quantum computing does not rely on conveying information via entanglement. It does use entanglement as a kind of faster than light signaling, but it's not signaling in the sense of sending information. We're not going to get into the details of quantum computing, both because you're tired of all this and because it's above my pay grade. But there is hope of using entanglement to speed up information processing, but it is not done via sending information. Nothing, so far as we know, can be sent faster than light. That's why it's tempting to view this as one system, one thing. The twin particles are one thing that could be separated by 10 million light years. And that way, what's going on here is when you perform a measurement on the first photon, you collapse that wave function everywhere in the universe all at once. And so it collapses at the other location instantly. But it's not a matter of something being sent. That's our current best understanding. If it hurts your brain, you are not alone. Chew on this, look at the DeWitt, replay this lecture if you need to, reread the DeWitt if you need to, formulate some questions, email them to me, come to office hours. I want you to understand this. On the exam, I'm going to expect you to understand this. And now give your brain a break. Thanks for hanging in there, folks.